the forces that we can do on atoms, right? So I'll write them quickly here. So we deduce that the radiation pressure force is just equal to what we have called a rate of exchange of photons times h bar k, right? And the dipolar force is just equal to, so the dipolar force is better to be identified, we better write it not as a force, but as a dipole. Okay, so as a potential energy. So the dipolar force is minus the derivative of a potential energy, and the potential energy is just equal to, let me take the exact expression here. So in the limit of Higg detuning, we have found that this is equal to 3 pi c squared divided by 2 omega 0 cube, gamma divided by delta times the detuning. Remembering that this 1 over delta, actually, if you, I'm going to write it 1 over delta star, to remember that this 1 over delta star actually is equal to 1 over omega minus omega 0 plus 1 over omega plus omega 0, if you want to really include the counter-rotating terms, which can be important if you are going to be really out of resonance, okay? So now, we have two kinds of forces, and those forces, they are relevant in different contexts, okay? We can, with them, create a whole bunch of different trapping and cooling schemes for the atoms. And based on those forces, we have since the 80s introduced all those cooling schemes, and still today new schemes appear. So I saw a poster on magneto-optical traps with different number of beams. So you see that still from time to time have a new original idea that can give rise to a new nice system to do some physics. It's true that today cold atoms is more like a platform. So it's still, you can do research on techniques for cold atoms. You can still find some things, but cold atoms are more used like a platform for studying different kinds of physics. You will listen about some of this physics in what's going on here. Now, I would want to discuss in order to discuss, to understand all some of those cooling mechanisms, we still need one or two more ingredients, okay? So the first ingredient that we need is the Zeeman effect, but I know that Irina has already talked to you about it, right? The Zeeman effect. So the Zeeman effect basically is what happens when you apply a magnetic field to your atom. So if you apply a magnetic field to your atom will interact with this magnetic field, and via a new Hamiltonian, which is just equal to minus the magnetic moment of your atom times the magnetic field, right? So now this Zeeman effect, what is the main effect on your atoms? It will split the resonances. You will be able to understand how many magnetic sublevels you have hidden in a way inside one specific level of your system. The magnetic moment of your atom in general is a function of 3 different magnetic moments. Your atom can have magnetic moment due to the orbital momentum of the electron, so it has magnetic moment associated with the orbital momentum L, plus it has magnetic moment associated with the total spin of the electrons, S, and you can also have magnetic moment associated with the moment of the nucleus, okay? Now, they do not have the same order of magnitude. So you have mu L, which is the magnetic moment related to the angular momentum, to orbital angular momentum of your electron. This is just equal to Bohr magneton times L divided by H bar. Wait, let me think if this is correct. No, this is, let me write it. This is correct, but I prefer, so it's better to write it like, so this is the electric charge of the electron divided by 2 times the mass of the electron times minus, because I have written E as the fundamental charge, which is negative, times the angular momentum, okay? So this is correct. Okay, so this is the magnetic momentum related to this is the mass of the electron. Let me just let me put E. Then you have the magnetic moment associated with the spin, so it's very similar times the spin of your electron, but you know that you have an extra term here, which is the gyromagnetic factor of the electron. So this gyromagnetic factor is approximately 2. Actually, you deduce that this is 2 if you do a relativistic model for your electron, and actually it's not exactly 2 because of corrections due to the interaction of the electron with the vacuum modes of radiation, and you have some terms here, I think 2, 0, 0, I don't remember 1 and something, and this is one of the physical constants that is better, that is measured with lots of decimal places here, I think 12 or something. It's one of the best known physical constants. And so, okay, it's not the same. And then you have the magnetic moment of the nucleus. So the magnetic moment of the nucleus is just equal to, it's also a factor that depends on the nucleus. I'm going to call the gyromagnetic factor of the nucleus, depending on the amount of protons and neutrons, it changes, but it's for each nucleus is going to be different, but this is proportional to the electric charge divided by 2 times the mass of a proton. Okay? So you see that this is very small. So this is going to be 1,000. So this is going to be 2,000 times smaller than those 2 other here, because the mass of the proton is 2 times higher than the mass of the electron. Okay. So this means that normally this is neglected. We don't take into account this, and so normally when you think about the Zeeman effect, you will just take into account the magnetic moment of the nucleus of the magnetic moment due to orbital momentum of the electron, and magnetic moment due to the spin of the electron. Okay, but the angular momentum of the nucleus, the E, enters into the calculation in a way because the eigenstates of your atom, they are a function not only of L and S, but also of E due to hyperfine splitting. So, of course, you have this magnetic moment. It's important for you to know which are the eigenstates. So, for example, you take rubidium-87, you have 2 levels, F, down there you have F equal to 1 and F equal to 2. So the F, what's F? F is just the total angular momentum, right? And F equal to 1 means that you have 3 magnetic sublevels here, and F equal to 2 means that you have 5 magnetic sublevels here, right? So here you have MF equal to -1, 0, 1, -2, -1, 0, 1, 2. And in the end, you need to take into account, you need to do a calculation in order to understand how you will, what's going to happen with this Hamiltonian here. So what's going to happen with the total angular momentum, total magnetic momentum of your electron, when the electronic state is in one of those states here, because those states are a combination of states of definite, of states of different magnetic, of different ML, different MS, and different ME. So different projections of the momentum L, S, and E in the Z direction. You understand this? So those are combinations, okay? So in the end, you can work out the calculations, and you end up with an expression which is not that complicated. The Hamiltonian is the energies. So if you apply a magnetic field which is small enough, such as the Zeeman state, the Zeeman shift is going to be much smaller than the separation between F equal to 1 and F equal to 2, much smaller than the separation between the 2 hyperfine states. So this is the separation here is just the hyperfine energy. So if you are in a situation in which the Zeeman energy is much smaller than the hyperfine energy, then you can write the Zeeman energy just as the Bohr magneton times the times a certain Landé factor, which is a function of the Landé factor is going to be a function of L, S, and I numbers, and you have the expressions on internet you can find. So you have the expression on Wikipedia, for example, or in any book, times the MF of your level times the magnetic field that you apply. Now here I am assuming that the MF, so that vectorial expression became here an expression which is a scalar expression, because I'm assuming that you are projecting the spin of your atom in the same direction of the magnetic field. Okay, so either you assume that the direction of the magnetic field is Z, and then you just Z is the quantization direction, but this is assuming that the quantization direction is the direction of the magnetic field. Quantization direction is the direction of B. Okay? So this establishes some, so I want to give quickly, I don't want to spend lots of time on this, but I want to give quickly some information on how now we have still not considered, up to now we have treated our atoms as two-level systems. So now you see that things are becoming much more complicated. I have lots of lots of levels here. If I count how many levels I have, just in the fundamental level of rubidium here I have 8 levels. And this can become worse. So the excited state, the P state has F equal to 0, 1, 2, 3. So if you do the math, you're going to have 16. I don't know if I'm 7 plus 5 plus, yes, 16 levels up there. So you see that you have lots of levels. And of course, it's not a two-level system. But we can, in a way, try to understand our this whole situation based on what we have learned from the two-level systems. So I just want to give one or two informations on how you can think on these more complicated systems, okay? So first, in order to understand which kind of transitions I can do with my light, I need to talk about light polarization now, of course. And I need to talk about selection rules, okay? So selection rules, you know that your light, when your light comes to your atom, okay? So before we were discussing about, we established a two-level system, and I just said, imagine that your light can couple the fundamental state to some excited state. Now we're going to ask ourselves, can the light couple this state to another state? So, and how can I discover if the light can couple two states? So I'm gonna, and so in order to see this, what I really want to know how to calculate, I'll go back a little and remember that it was important. What we had in the really beginning was just the levels of the hydrogen atom. So hydrogen atom. I'm not putting hyperfine state. I'm not putting spin. I'm not putting angular momentum of the nucleus. I just have this now. Right? So in the hydrogen atom, I go back to a situation in which I pretend there's no spin. Of course, there is spin, but okay, there is no spin for now. So in the hydrogen levels, you have three quantum numbers, N, L, and ML. And in order to know if the electric dipolar Hamiltonian can make a transition between two levels, I need to calculate these elements, these non-diagonal matrix elements, right? So this is what I need to calculate. Now, remember that the Hamiltonian, the interaction Hamiltonian is, dipolar Hamiltonian is minus G scalar E, so we can write this as E R scalar E, right? So what's important here? So this is the operator that will act between those levels. So what we need to calculate in the end is terms in the form n, l, ml, x or y or z times n prime, applied to n prime, l prime, ml prime. So this is what we need to calculate, right? So if we know how to calculate this, we know the transition elements. Okay, so this is easy to calculate. I mean, quite easy to calculate, but I'll not calculate this on this basis. I'm gonna do a small change of the basis change. I will, instead of describe the polarization, so you see that here, depending on the polarization of my light, I will select one of the directions of the dipole here on the operator. If my light has polarization in x direction, this will select the x dipole moment here, and y the same, and z the same. But I'll not describe this in this linear polarization basis. I will prefer this polarization basis here. So I'll choose to note the vectors like this, because these for me are the operator x, operator y, operator z. So this on the contrary, this is those are the vectors of unitary size. Okay, so e x times e y is 0, e x square equal to 1, etc. Okay, so those are the vectors that define the three directions of space. What I'm doing, I'm writing something completely, I'm sorry, sigma plus, sigma minus, and pi. Okay? And I also put, sorry, I'm going to put also vectors. So those are three bases for the polarization. So here is just polarization in z direction. This is linear combination of x and y polarization. Okay, so what does it mean? Linear combination with an imaginary vector. So this makes sense in a complex representation of the electric field, right? So if I say that the electric field complex is equal to E0 times sigma plus e to the e kr minus omega t. So the electric field is really the real part of this electric field. And if I take the real part, you can work out, you're going to find that this is E0 times cos of kr minus omega t. Let me put already here the plus or minus. And then this is going to be in the x direction. And then the e, so minus plus sine of kr minus omega t in the y direction over square root of 2. So this means that this is just circular polarization in one direction or in the other direction, okay? So those are the two circular polarizations. Okay, so then, okay, so if I write the electric field in this basis, now let's see what a circular electric field can do on my atom. So if the electric field is purely in the direction, purely circular in this basis, I'm gonna write this. So let me call this electric field plus or minus, and let's work out for electric field for this electric field. So the Hamiltonian, the Hamiltonian is just gonna be equal to where am I? Sorry. Yes, okay, I'm sorry. So this is equal to, so the Hamilton is just equal to D times E plus, and this is going to be equal to, so the E plus is just there, and the D is just equal to X. So it's a vector, it's E minus E times the vector R, right? So this is, if we do the product here, just gonna find that this is equal to E0 over square root of 2 times X cos of omega t plus Y times sine of omega t. I'm dropping KR equal to 0, okay? And you can rewrite this as E plus over 2 times e to the minus E omega t X plus EY over square root of 2 plus e to the E omega t times X minus EY over square root of 2. Okay? So, okay. Now, I have rearranged. I have opened this as e to the E omega t plus e to the minus omega t, and I think the same thing I have done there, okay? So, it's good to open it like this because I know that this term here and this term here is going to excite, those can be resonant or non-resonant depending on what I want to do, okay? What happened to the minus? It's a good question. So let me see what happened to the minus. Let me think about this minus so we can understand what happened to the minus. So, because I don't have the minus in this expression, so let me see. This is that. But I agree. Yeah, but I agree that the sign is exchanged here, right? So let me think. I know what happened to the minus. So this is minus omega t. So there was a minus sign, and here I got wrong. So it's minus I with plus I, and this is plus and minus, and not minus and plus, okay? And so, no, but okay, no, yes, no, okay, I'm sorry, again. This is good, I'm sorry, this is good, but when I'm gonna do this equal to 0, this is sine of minus omega t, which becomes another minus here. This is, okay, so this is what happens. It was good, but then this is the question. Which minus then? Oh, the minus here. Okay, because I forgot this minus here. Okay, yeah, okay, yeah. What? Let me finish the calculation, then I'm going to tell you why I chose, okay? So, okay, so then this is the case. And now the question is that you see that here, so you see, I don't see, now I see. So here you have two terms. Remember that you have this story of, so there are terms that are resonant and terms that are not resonant with the transitions. And if you remember back there, you are gonna, when we have written the Hamiltonian in the dipolar approximation, we have written that this is h bar, I'm sorry, in the rotating wave approximation, this is equal to h bar omega 0 divided by 2 times e to the E omega t times sigma plus e to the minus E omega t times sigma minus, or the opposite. Let me see. The opposite. So this means that the term with the minus here is related to exciting, and the term with plus is related to de-exciting my atom. Okay? So actually, this term here will just be resonant for going from the lower state to the higher state. And this term here will just be resonant to going from the upper state to the lower state. Okay, so actually, this in principle can do both, but in the end, it's going to be non-resonant if it acts from higher to lower. So I will consider that this term here is the term that will be important for me to excite the atom. And this is going to be to de-excite the atom due to the fact that I know that energetically, the term that turns with minus e omega t is the term that will just be efficient for exciting, because otherwise the phase would turn with 2I omega t, and this is not important, okay? So I am going to observe here, I'm just going to use this just to excite. This is de-excitation. So, everything I need to calculate now is, in order to know how this acts on my levels, I need to calculate this. Okay? This is just an integral, which is a very big integral. And this integral, it's going to be made of, this is an integral which is I'm sorry, so this is times, this is what I have to do. This integral here is actually equal to a radial part, which I will not write, and this is going to be times a angular part. The angular part is going to be integral from 0 to 2 pi in phi equal to 0 and pi sine theta d theta, right? Times. What's the angular part of this? The angular part of this is the spherical harmonic. And then the angular part of this is this. And then what's that? I'm sorry, this has no operator anymore. So this, you can show that this is just equal to r sine theta times e to the I phi divided by square root of 2, and this is equal to minus square root of pi 4 pi divided by 3 times r times e11. So the angular part of that, apart from a factor, is this. And so this is just going to give to you, so here if you do this calculation, this is going to give to you just this angular integral here is just equal to the angular part. I'm going to call E with indices L1, L prime, ML, M, ML prime, and you have some symmetries on this integral, and this integral M in this case is 1 ML prime. The integral of this shape is different from 0 only if L minus L prime is modulus of this difference is equal to 1, and if ML prime plus 1 equal to ML. I'm sorry, ML plus 1 equal to ML prime. No, I'm sorry, it's the opposite. ML prime plus 1 equal to ML. So what does it mean? This means that you have deduced selection rules for a transition with sigma plus. So let's say that I have a level here with a certain L, and a level here. This means that I can just go with So if I have a level with a certain L, I can just go to a level which has L plus 1 or L minus 1. So L plus or minus 1. So you can have more levels or less levels here. So this means that this selection rule here means that you just can go to a level from a level S to P. The level P can go to S or to D. Level D can go to P or to F, etc., 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 by electrodipolar transitions. Because you can just change the L by 1. So you cannot go from S to S with one photon. You can not go from P to P, P to F, etc., etc. And this just means also that the sigma plus light, remember that I am considering the transition to excite. So the sigma plus takes the atom to a level with angular momentum plus 1, which is just, you can consider this is energy conservation, okay? Angular momentum conservation, okay? Now, if I would consider what does the sigma plus polarization do to de-excite? So to de-excite, I need to consider the integral with this term here. And this term here I can show to be proportional to E1 minus 1. So this means that the selection rule will be opposite. So the selection rule, this is M, so this is M. So the selection rule will be opposite, because if M equal to minus 1, this means that if this is equal to minus 1, I will reduce my level. So the sigma plus can also do this. So the sigma plus couples these two levels, and only these two levels here, okay? Now, if you work out the expressions for sigma minus, of course, you are going to find that this is happening. This is what sigma minus can do. And if you work out the expression for pi, you can show that pi will have the same selection rule. So a pi polarization also needs to bring S to P, P to D, and D to F, cannot bring S to S. But the pi, in terms of the magnetic moment, in the Z direction, can only do this kind of transition. Now, you can ask me, what does it mean? 3 different polarizations, because light have only 2 polarizations. But see, all this calculation was done in considering a fixed quantized direction. So all this polarization is with respect to a fixed direction Z. So if I send light in the Z direction, sigma plus corresponds to positive helicity, sigma minus negative helicity. What's helicity? Helicity is the polarization of light projected in the direction of the wave vector of light. So if the light is propagating in plus Z direction in this model, helicity of light corresponds to polarization. So sigma plus is positive helicity, sigma minus is negative helicity, and pi I cannot do because pi is polarization like this. I cannot do with light propagating in Z direction. If the light is propagating in minus Z direction, it inverses. What we call helicity, its polarization in the direction of light propagation is going to be the opposite of what I'm saying. So light with positive helicity actually means sigma minus in the basis, in the quantized basis of plus Z, and etc. And I still cannot do pi polarizations. Now, how can I do pi polarization? Well, let's send light in the Y direction, for example. If I send light in the Y direction, and I'm describing my atom in the Z polarization, now, in the Y direction, the linear polarization like this is Z. And what's linear polarization horizontal? In these bases that I have written. So I'm sending light in the Y direction, and I can write, for example, linear like this and linear like this. So this is Z, and this is X. So this polarization in X direction is just a combination of sigma plus and sigma minus, okay? So if I send light in the Y direction, the vertical polarization will be able to do this, and the X polarization will be able to do a combination of this and that. Will excite, actually, it will excite a linear superposition of these two levels with the right phase, okay? So you can always know what your light is going to do. You just need to think a little about the polarization of the light and project on the polarization on the basis you have chosen to describe your atom. Of course, it's easier if you choose to describe your atom in the same, if you take the polarization basis to have quantization axis equal to the propagation direction of light. But sometimes you cannot do this, because if you have applied a magnetic field and your atom has already the levels shifted, then you send light like this, you need to think in the other basis, so you need to be calm, okay? Now I'm doing this only in the, I have not considered the magnetic sublevels. I mean, I have not considered the total angular moment of the atom. Now, if I include the total angular moment of the atom, you can ask yourselves whether those calculations are still valid, and there is something is still valid and something will be modified. So now let's consider, for example, a rubidium transition. Let's consider a rubidium transition from F equal to 1 to F prime equal to 2, for example, the D2 line. So this is 5s 1/2, this is 5p 3/2, okay? So you have here 3 levels, and you have here 5 levels, right? But this is not just a level, this level do not have a fixed ML, for example. Here you have a fixed MF, which is a combination of levels with ML, MS, MI, okay? So what's gonna happen is that by angular momentum conservation, those selection rules are still valid. So now if you just replace this by MF, these selection rules are conserved. So sigma plus will just be able to do this. Sigma minus will just be able to do this. And pi will just be able to do that. Okay, so it's still fine, this still works. But now, the dipole moments are not going to be the same. So if you send light, so the Rabi frequency that you are going to do here is 1 Rabi frequency. This is going to be another one, and this is going to be another one. In general, you can show that the coupling here is stronger than here and here. So it's more Rabi frequency for the same. I'm saying that for the same light intensity, the coupling here is stronger than here and then here, because the omega 0 is d times E over H, and since you just couple to the this here is still the R of the electron. So actually your light can just couple to the orbital variables of the electron, to the position of the electron, not to the spin. So the dipolar approximation means that you don't not couple to the spin. So this means that since you have different combinations of ML here, you have different coupling intensities here. But still you preserve the selection rules, okay? And you also have different decay rates to all those levels. But again, by symmetry, there is a sum rule that says that the total decay rate from each one of those levels is always equal to gamma, the total decay rate. It's just that you're going to fall in some different levels with some weights, and you don't really know. I mean, you can calculate. It's complicated, you can calculate, but but it's complicated, okay? You know, you can understand, but every time the total decay rate is gamma. Doesn't matter from where you decay, okay? So some things are equal, some things change a little, okay? So this is really technical. But I mean, I think can be useful for some people. So I wondered if I should say or not. I mean, after you can come to me and say if you think it's useful or if you think it was stupid to pass lots of time talking about this. But those things are so those things are things that you in the lab you need to know, and if you do atomic physics, and it's. Yeah, okay, so you need to do the math, okay? So you have these two selection rules, and now then we can understand how we can do several different trapping and cooling mechanisms. So I will begin with the simpler one, which is, so, okay. what you can, it's okay, maybe simpler than the molasses is how to cool down an atomic beam, okay? So if you have an atomic beam with high speed, so high velocity v, okay? Now, and also not just velocity v, but you can also have a distribution of velocities. So you can have the distribution of velocities. Yes, so you can have a beam with a central velocity and a distribution of velocities around the central velocity. Okay, so you have lots of different atoms, and you want to use those atoms to prepare to prepare a cold atomic sample. Okay, so what you can try to do is, okay, let's try to send some light here. So I'm going to send some atoms, some photons against those atoms, and I'll try to stop those atoms, okay? But you can show that this is not going to be very effective because you will just be talking to atoms in a quite narrow velocity range. What's the velocity range where you talk to your atoms? Is just around gamma divided by k, right? Now, you can saturate your transition. If you saturate your transition, you can be a little better. You can do this is what you can do if you saturate your transition, right? So the transition gets broadened, and then you have a broader width, but you see that it's harder and harder to saturate because the width just increases as the square root of the intensity, and so in order to see 2 times more atoms, you need to put 4 times more intensity, and at some point you can just not talk to all the atoms at once, okay? So it's not practical to saturate to saturate a transition such as to reach the full Doppler broadening, okay? So the delta V we can estimate quickly for rubidium atoms again. So let me just take the delta V non-saturated. So 2 pi times 6 megahertz divided by k. K is 2 pi divided by lambda. The lambda is 780 nanometers, okay? So 780 nanometers. So this is, you see that this is just equal to around 5 meters per second. So delta V is just 5 meters per second, but typically for room temperature, kBT divided by M is on the order of, I don't know, 200 meters per second, or, okay, so I'm sorry, so square root of kBT divided by M is on the order of hundreds of meters per second. So you see that you just talk to a tiny fraction of your thermal atoms if you try to send some beam, okay? So something you can do is enjoy now that you have Doppler shift, but you also have Zeeman shift, and you can do what we call Zeeman's lower. So what's a Zeeman's lower? A Zeeman's lower is a kind of arrangement in which I will try to compensate for my Doppler effect by applying a magnetic field. Okay, so Zeeman's lower. So it's very simple. It's used in lots of labs. It's used in our lab in São Carlos. So what you do is you're going to do the same thing as you are doing there, but now the atoms are coming here. The light is coming from this direction. And then on top of that, you have like some coils, magnetic coils. And then you do the magnetic coils in a smart way, such as to produce a magnetic field that will vary on time. Let's imagine that the magnetic field grows quickly here and then goes varying on time like this. Okay, so this is B as a function of the position Z, for example, and this is Z. Okay, so we have a varying magnetic field. Now, if I write the resonance condition for my atom, yeah, and I'm going to be smart here also. I will need to send light in a specific polarization, and let me think which polarization is good. So I need to send sigma. Okay, I'll write something, and maybe I'm going to be wrong, and then we'll discuss. let's say I send sigma plus, and if I'm wrong, I'm an experimentalist, I just have a wave plate I change. So I'll try to send sigma, I'm sending sigma plus polarization. So this is polarization considering the quantization direction plus z. I'm thinking about plus z because the electromagnetic field is measured in plus z. So now I want to measure the detuning. I want to calculate what's the detuning of my atoms. So the detuning is every time the frequency that my atom sees of light minus the natural frequency, okay? But now I have two differences here. First, the atoms have a velocity v like this. So this means that they don't really see omega. If I'm sending here light with frequency omega, they are going to see something which is omega, and they are going against light, so they're going to see omega plus kV, okay? That's the first thing. Second thing is that natural frequency, it's not omega 0 no more, because now I have some magnetic field. So now, if I send light with sigma plus, and let's do some very simple situation here in which I have a transition from j equal to 0 to j equal to 1, okay? So let's do something simple. And so I will have here this transition. Let's say that I'm talking to this transition here. So this transition, so this is mj equal to 0, this is mj equal to 1. So the Zeeman energy is just going to be equal to μb, so times jg. This guy is going to be shifted by 1 plus 1, so I'm not including, times b. Okay? So this is the Zeeman shift. This means that omega 0 prime is equal to omega 0 plus, so I'm shifting the excited state, so plus this. Okay? No. So I'm gonna. So for me, sigma plus and sigma minus is. I always, when I say sigma plus, sigma minus, in my head, I'm thinking from the point of view of the atom. So sigma plus does this transition for my atom every time. Now, in order to make my light do sigma plus, if I want to make this transition on my atom, you really need to think about which helicity you need to put, because you're projecting one basis, but you see, so I mean, it's just like, I'll put my polarization analyzer, I see a R there, right? Oh, I'm good. Maybe not. You need to think twice. Okay, so this is often the case when you do some MOT or you do some magnetopical trap. So every time the polarization is in the lab, everyone is like, you enter the lab, everyone is like this, trying to figure out what they should do, and in the end, what they do is that they do something, it does not work, they change to the opposite, and it works. So it's, because it's very hard to guess. You always have 50% of chance of guessing from first. But it's just to explain to you that you need to be careful. Polarization is hard to guess because you have this change basis, and okay? So, in the end, yes, for experimentalists, we'll try both. This is the easiest thing. You put a number over 4, 90 degrees after you circularize to the other, and try both. So, okay, so you also have a shift from here. So now if I have everything inside, you have that delta is equal to, is just equal to omega plus kV minus omega 0 minus minus the Zeeman shift. So if I call omega minus omega 0 delta 0, which is what's delta 0? Delta 0 is the detuning for an atom at rest with no magnetic field. So mega minus omega 0 plus kV minus this. Okay, and I think I guessed right what I should have sent, because I have sent sigma plus. Sigma plus means that here is a plus, and this is good because, see, what I'm gonna do now, how can I make my Zeeman lower work? What I'm gonna do is that, here in the beginning, so I'm gonna send light with some frequency, and here, in order to match, so I have a maximum of the magnetic field here, and I will make the magnetic field compensate for big velocities, and I'm gonna talk to atoms which have high velocities. So they will decelerate a little. What I'm gonna do with my, with this velocity distribution here is that I'm gonna open a hole and do something like this, okay? But then they have accumulated here, and now my lights do not talk with the atoms anymore. But then they continue traveling. And so they're going to experience a smaller magnetic field. So now for a smaller magnetic field, the detuning is 0 for atoms with smaller velocity. And then I cool those atoms too. And in the end, what I do with my curve is I do something like this. So those atoms are lost for science. I cannot cool them really. Now I do this. Okay? And I'll keep going like this, and the atoms keep accumulating until in the end I arrive with some cold atoms. I must be careful. I must think it through, because if my magnetic field goes down too much, I mean, if the resonance goes down too much, I can be resonant with atoms at rest, and then I make them go back. I make the velocity negative. So this is not what I want. Okay, so I need to arrange the frequency that I send and the magnetic field profile in order to make the most of it without sending all the atoms backwards, which it's not what I want. And like this, I can arrive in the end here with an atomic beam of nicer. If I am good, I have lost some hot atoms, and then I have some atoms cold enough in order to load my magnet to optical trap or the next cooling stage. Okay? So this is something you can do to cool an atomic beam. So this is even slower. Okay, so this is very common. Okay. Now, there are other cooling techniques. So this is a good cooling technique for if you want to cool in just one direction and you want to cool atomic beams. Now, so there are other cooling techniques that are not as efficient to cool from room temperature, but from the temperatures that I can achieve with this Siemens lower, this first stage, I can already install this second kind of cooling technique, which is called optical molasses. So I think you have all heard about it. Now you know from where molasses come from, the name. I think you know also. So molasses, I'm not good in English, but what I have been told is that molasses is like, at least this is how we think in Latin, in Portuguese, molasses is as when you walk inside honey. So you walk inside a very, so at least in Portuguese we call it melaça, which is good because mel in Portuguese is honey, and for us we associate this with walking inside honey, which is very hard because it's very viscous, right? So the idea is really to create an environment for the atoms with a very strong viscous force. What's the characteristics of a viscous force? A viscous force acts against your velocity. If you want fast like this, right? It's a force which is proportional to your velocity. So optical molasses. What we really want to create with an optical molasses is a force which is like this, with beta positive. Why this kind of force is nice? So if we consider the work that this force does, so we can calculate the power of the work of this force. So the power of the work of this force is just F times the speed of the velocity of the atoms, right? And if I install this inside, this is just equal to minus beta V squared. So you see that this kind of force is always doing work against your atom. So this means that this kind of force will always remove kinetic energy from your atom. And if you ask yourself, what's the equilibrium position, it's not position because this is not conservative, but what's the equilibrium situation for your atom? The equilibrium situation is when the atom is at rest. So you see that in theory, I mean not in theory, but by just looking at this expression, we would be able to cool atoms until 0 temperature. Now, of course, we know from third law of thermodynamics that this is not quite possible. There will be some mechanism that will prevent us from doing this, but it's pretty good. We can go to pretty low temperatures if we have this kind of force. So now let's see how we can create a force like that, okay? So in order to create an optical molasses, I'll just go, you just need to think, so you just need to think, let's first do a 1D model. And in this 1D model, so in this 1D model for optical molasses, what you have is that you will consider that you're going to send two different beams like this and like this to your atom, and so your atom is a 1D model. So let's put here the z direction. Here you have h bar. So here this h bar k, let's call k plus, and h bar k minus. So k plus is just equal to k in the z direction, and k minus is just minus k in the z direction. So you send two counter-propagating beams of frequency omega, and you're going to consider your atom with a speed v, which is also going to be in the z direction because we are doing a 1D model. So everything happens in 1D here. Then we can, it's rather easy to extend it to 3D situation, okay? Something that I should have said here is that, so here, what am I using to cool the atoms? So here I am close to resonance, okay? So what's the important, I'm always talking here about exchange of photons, etc., etc. So what we are really using here is the radiation pressure force, right? So here we are not talking about dipolar force. So these forces are, those forces are not, how to say, conservative, okay? But we don't really care. But so the important component here is radiation pressure. We are using radiation pressure all along. And here again, for the molasses, we will be close to resonance. So what we'll really be using is radiation pressure. So now I want to write the expression for the force created by each one of those beams. So I'm going to call the radiation pressure force created by this beam F plus, and the radiation pressure force created by this beam F minus. And so let's see how each one of those expressions are. F plus is just going to be equal to, remember, it's just the exchange rate of photons times h bar k plus. So the exchange rate of photons is equal to, this is equal to S0 divided by 1. So the exchange rate is just equal to the excited state population times gamma, and the excited state population is just equal to 1/2 S0 divided by 1 plus S0 plus 4 times delta divided by gamma squared. Now, delta, in this case, I don't have magnetic field, but I do have Doppler broadening. So delta for me is just going to be like this, okay? So, and I need to be careful because if I consider V in the direction EZ there, so you see that what's going to happen. So, okay, I'm going to write it. I'm going to write it here. Delta plus is going to be equal to omega minus omega 0 plus the Doppler, which is kV. Let me think if I. Yeah, okay. So I'm sorry. I need to make to make a correction here. I'm sorry about this. So I'm sorry, you are going to correct. As I have written here, this is wrong. I'm sorry. Because when I put the product like this, I should have a minus. Now, what I really wanted to write is this. Because I was considering the directions, and I was just, I'm sorry about this. So this is wrong here. This is wrong here, okay? So because I have already done the product, and the product has a minus sign because in my drawing they were opposite. I didn't want to put this. Actually, in all cases, the Doppler is just this. In all cases, this is the Doppler, okay? And then the relative direction is inside there, okay? So I'm sorry, I have already thought about the opposite direction, and there was a plus. But I should not have put the, okay? You understood what my mistake? Okay, so now it's fine. So, but then this is every time the Doppler broadening. So, and this, of course, then this is wrong. And then in this case, K plus scalar with V is plus K times V because they are in the same direction. And so this is just, so this is plus, and this is just going to be equal to delta 0 minus KV, okay? So I'm going to put this inside. Plus 4 delta 0 minus KV divided by gamma squared times H bar K in the direction Z, okay? So this is F plus. And how is going to be F minus? F minus is just this times K minus. And then you also have, I need also to say that you have exchange rate of photons with the other light. It cannot be the same, can be different because you have Doppler now. And then delta minus is like this, and it's going to be with a plus here. So this means that a plus here, okay? So the total force is equal to F plus F minus. And I'm not going to write, but you see that it's the sum of both forces. Now I can make a nice graphic to try to understand how this works. I'm going to do, note now that this force is a function of the velocity, okay? Of the speed v. And so I'm going to write, I'm going to do here the force as a function of v. Okay. So, and I'll be already, I'll draw this graphic already in the situation of delta 0, because this is the relevant situation for us. You're going to understand why in a second. Delta 0 negative, okay? So this means that the frequency of light is smaller than the natural frequency of the atom at rest. So at rest, the light is below resonance, okay? Okay, so I'm going to draw those two forces. So you see, and something that I forgot here, I'm sorry. So the K minus in the opposite direction. So there's a plus and minus here also. Okay, so I forgot this. So no one is correcting me. You just let me say horrible things in front. And okay. Anyways, so I think now is correct. Let's see if the drawing does not go right, then I'll find some other mistakes. But I think it's correct. So okay. So let's draw the F plus in this situation here. Okay. So F plus is always positive. So it's going to be positive, and the dependence on the speed is just a Lorentzian. Okay, it's just a Lorentzian. Lorentzian dependence on speed. Centered where? So this is centered. So for the F plus, this is the minus here. And so the situation of a maximum force is going to happen when delta 0 minus KV is equal to 0, right? So this means that V is equal to K divided by delta 0. But I'm taking delta 0 negative. So this is equal to minus K divided by modulus of delta 0. Okay? So this is for V plus. This is the frequency, this is the velocity that for an atom to be resonant with the force V plus. So it's it's wrong. I don't understand. This one here is yes, of course it's wrong. I'm sorry. Thank you. Of course. Okay, thank you. It's not even dimensionally correct what I'm writing now. Okay, thank you. So so let's check. We can check if it goes, if it's fine. Yes, okay. It's normal that the speed is negative because since I am below resonance, I need to go against the beam in order to see the beam with higher frequency and be resonant. So, okay, I got it right. So this V plus is here. So the force is just be a Lorentzian centered around this V plus, right? So it's going to be something like this. Okay, so the maximum force we can calculate is just equal to this 0 is just equal to population times, right? So the maximum force here is just equal to sigma E gamma, that of course I forgot, and no one remember me that I forgot, times h bar k, the maximum force here, and sigma E in 0, right? So this is okay. So 1, 2 S0, 1 plus S0. The width is just related to the Doppler width broadened. So this width is just equal to gamma square root of 1 plus S0 over K. Okay? Now for the F, this is F plus. This is F plus. Now for F minus. F minus first is overall negative, and second, F minus, it's going to be maximum in modulus for the speed with opposite sign, right? So it's V minus is equal to minus that, so it's equal to B with a plus here, right? So this means that this force is going to be, so this is V minus here, and then the force is going to be like this. It's the exact same thing, but it's inverted and it's shifted. Okay? So how is the global force? So this is the total force, right? So it should be crossing 0 here. So it's a little wrong. So this is the total force. And around here, the force is of the like minus beta V, with beta positive, okay? So I can, so then this graphic is nice because you see that you can estimate what would be the good parameter range for molasses. So if you have, you see that if those maxima and minima are too far away, actually here where I will have a slope which is ridiculously small, right? So I don't want those to be really far away. Actually, the best thing would be to have this comparable to the width, okay? So this means that I want the tuning comparable to gamma, okay? So you can calculate that the best one in the simple model, I think the best tuning is equal to minus gamma, or minus gamma over 2, remember. So it's on the order of gamma, but due to other effects, normally for alkaline atoms, you want to go further away. You have 2 gamma, 3 gamma. Well, depending if you are in potassium, all levels are mixed, so potassium, I don't know. But it's complicated. But for rubidium, normally it's minus 3 gamma. For strontium, because why? Because atoms with hyperfine, because then we need to discuss about the limits, temperature limits, and then you have some effects. We're going to discuss about this in some time. But you see that in general, you want to be on the order of delta. So another thing that you can check is that if you increase your intensity, light intensity is good because you increase the height of those peaks and then you increase the slope. But then if you increase too much, you stop here, you saturate, and then you just increase the width. And then the slope again is going to be a little bad because then you begin to saturate. So the intensity also, you want it big but not that big. So you see that with this kind of simple reasoning, you can understand in which kind of parameter regime you need to be in order to cool your atoms. Okay. In a simple situation, you can so if your velocity, so you can guess what's this beta here around here if you do the expression for the total force in the limit of v tending to 0. Okay, so you can do this approximation. So you just need to expand this in first order. Okay, and you are gonna find, and then you can have an expression for beta. Okay? And you're indeed going to find that the force is equal to minus beta v, and beta, I'll just give to you the expression. You will accept. So, beta is equal to minus 8h bar k squared s delta gamma divided by gamma squared plus 4 delta squared. So S is not the saturation parameter is in resonance. It's really the saturation parameter detuned. Okay? So this is your beta. Okay? You can find it if you linearize the expression there. And okay, so this is, I'm sorry, this is what I call delta 0. And you see that beta must be positive for this to be good, right? And so beta is positive for negative delta. Okay? So of course, if you pass to positive detuning, what's going to happen? This, and the slope is positive. What means positive slope? Means positive force when the atom has positive velocity, so you hit your cloud. So it's not good to be, okay? Sorry? It's also delta 0. Yes. It's also delta 0. Yes. Mm-hmm. The fraction. Of course. Thank you. All delta 0, and I see that it's wrong on the notes. I need to correct. Okay. Well, as I said, so it seems that we can cool it to to 0 temperature, right? Of course, this is not correct, and I can say just one or two words about cooling limits. So you have so you cannot cool it. There is some limit due to the fact that what we are considering here really is just the average force of the atom on the atom. Okay, so but this force has already fluctuations. I'm not gonna do the full model. I'll just flash to you the result. So, but where do the fluctuations come from? They come in the simple model from the fact that while the force due to absorption is deterministic, so deterministic, I mean, not deterministic neither because you don't know exactly when you absorb a photon, but it's every time in the same direction. But then when you emit the photon, you don't know which direction it goes, so it's every time you receive a kick, okay? So you have two different limits coming from this simple idea, okay? So the first limit is due to, so you can write you can write a kind of kind of statistical reasoning about fixed force, cooling force plus fluctuation term, and you will end up in you can calculate the equilibrium temperature of this system subjected to force plus fluctuations, and this equilibrium temperature is given by, I'm going to give you the expression just, this is called the Doppler limit for optical cooling, okay? So the Doppler limit for optical cooling is just given by, I'm going to write it here. So Doppler limit, for those who are interested, there is a reference in the notes that you can read in detail. They do the calculation. Doppler limit for optical cooling, yeah, okay. And this Doppler limit is just equal to these times, so 1 plus 2G S0 plus 2 delta divided by gamma squared to, okay, so where D is the dimension of the molasses. Because I have just talked about 1D molasses, but of course now if you send beams in the other directions, you can cool in all directions, okay? It's just that if you saturate your transition, it's a little more complicated because the saturation of one transition will make that the others are not excited as good, and so the force, you'll not be able to write the total force as an independent sum of forces if you are in a saturated regime. It's more complicated than this, because if your atoms are doing this transition here, you have less atoms available to do that transition, so you cannot, when you saturate all transitions, it's complicated. But you can still have some kind of some force which is like that. But now beta is going to be a little more complicated. You understand? Okay. So this is the general limit, and if S0 is much smaller than 1, or if you are non-saturated, you see that this is where you reach the smallest temperature. And then you can also find the optimum delta to reach the smallest temperature. So the optimum delta is, you can just derive this and make equal to 0. And the optimum delta is going to be delta equal to minus gamma divided by 2. And you find really the minimum possible Doppler the minimum possible Doppler temperature, which is this, okay? And this minimum possible Doppler temperature is, okay. Okay, so I was looking at but this clock is not giving the good, okay. So the minimum possible temperature is this one. So this is called the Doppler temperature and is related to the width. You can intuitively understand this by saying that what you can think is that when the atoms are, when the atoms reach this small temperature, they arrive to a situation in which so they are to a situation in which they cannot anymore. So they are here and they are seeing the equal detuning from one side and from the other, and they begin to not be sensitive to the difference to the difference in detuning anymore. So it's more or less an intuitive argument. So you begin to be insensitive to the fact that to the fact that you have different detunings from one beam and from the other, and combine two fluctuations, you can find this Doppler minimum here. Okay, so now this Doppler minimum is really the minimum for strontium atoms, for example, because bosonic strontium atoms from the fundamental level, really the fundamental level of strontium has total spin 0 because it's a singlet state, 2 electrons in the singlet state with total spin 0. The angular momentum of the nucleus is also 0. And since it's a S level, L is equal to 0. So this is really a non-degenerate fundamental level. And the transition to the 1p1 state is really a J equal to 0 to a J equal to 1 transition. Okay, so this transition here really follows everything that you are saying here closely, and the Doppler limit is satisfied. If you have at sorry, so I forgot the name. So rubidium alkaline atoms. If you have alkaline atoms, you have hyperfine moment in the fundamental level, and you have other kinds of cooling mechanisms. You have, in principle, some. When you have hyperfine moment, what happens is that if you when you send, you see that I have not talked about light polarization here, but if you have hyperfine moment, the light polarization is going to be relevant. And if you, depending on the light polarization, let's say if you send light polarization like crossed like this, you will create a polarization grating seen by your atoms, because in a certain position you have circular plus, and then if you walk a little more, you have the phase of both are the same, so you have diagonal, and then the phase of both is shifted, so you have circular minus, and then you walk again, this is the polarization, so you have a kind of polarization grating. This means that atoms here will make transition sigma plus, atoms here will make transition sigma minus, and you have a kind of landscape like this, where the atoms will be, and if the atoms do transition sigma plus here, they can be pumped to a dark state, which is a dark, so if you do you make sigma plus, you can end up in a state where you are not pumped anymore, so you are in a dark state for this polarization, then you have dark states for the other polarizations, so it's somehow complicated, so you have this system of dark states that makes that your atom can accumulate in a dark state, cool, very with a speed still smaller than this limit, and then you can cool further your atoms due to this complicated hyperfine pumping, which is different in different situations. So I'm not sure about which kind of, I don't remember which kind of polarization is good for this, but you have some strategies, and this is called Sisyphus cooling. Sisyphus cooling. And so if you calculate this limit for rubidium, this is typically on the order of, the minimum is like 200 microkelvin, but you can easily go to 200. It's a little smaller. I think it's not 200. It's more like 100 and something microkelvin. But with Sisyphus cooling, you can go down to 20 or 10 microkelvin sometimes. If you can reach 10 microkelvin if you are careful enough with your molasses. So you can go below this. Okay. There is another cooling limit. Which normally no one talks about because you do not reach. But for strontium, again, it's relevant because strontium, the transition I have drawn is the broad blue transition of strontium of the gamma equal to 30.5 megahertz. But you also have, as I said, the narrow transition to the 3p1 level of a gamma equal to 7.4 2 pi times 7.4 kilohertz. And then this transition has a really small gamma. So you see that the Doppler limit for strontium, actually the Doppler limit for strontium is hundreds of nanokelvin. And then there's another limit that becomes important. It's called the recoil limit. What's the recoil limit? The recoil limit comes from the fact that light is not continuous. So in this model we don't see, but light is made of photons. And actually every time that you absorb a photon, you absorb a quantized momentum. So then you have quantized kicks. And what you are doing in momentum space is really, every time you receive a photon and you re-emit a photon, you are having a kick of a definite size in momentum space, okay? So this makes a kind of discretization. Now, you are trying to cool. This is the momentum 0, but you cannot really go there, okay? So there is some kind of limit just due to the fact that the momentum of the atom, of the photon is limited. So this gives recoil. So this gives recoil limit. So recoil limit for temperature. So recoil is just the effect that you have, when you shot a gun and then poof, you get the momentum kick to the other side. So when you emit your photon, you have a kick. So this is recoil. So, and this recoil limit, you can estimate. So you say that the minimum kinetic energy that an atom can reach is on the order of the momentum of the photon divided by 2 times the atomic mass. Momentum of the photon squared divided by 2 times the atomic mass. And if you say that this is equal to kb times the recoil limit, you find that the recoil limit is going to be like this, h bar k, h bar square k squared divided by 2 m kb. Okay? So this is a limit that usually is in the hundreds of nanokelvins, but for the strontium narrow transition, this is on the order of that. It's still a little, this is still a little higher, but not that much. So this comes into play. And if you go to still narrow transition, then you're going to have, you have to deal with the recoil limit. Okay? So I think I'll not, yes, I went a little slower than I thought today. So I think I'll not enter in the MOT, because otherwise it will take me some time and I'll just keep you here. I just want to, let's hope that will not take minutes. I don't know if I succeeded in turning it on. Well, anyways, I can show you later. I'll just show you some images, but it's, okay, it's MOT images, so I will just pretend that they were molasses, but they're really MOTs. So I will skip this and show last time. So it's fine for today. Okay, so it's the end.